Hey guys, I'd like to talk to you today about the simulations. In particular, this will be the first of three WebExes helping you understand what you're supposed to do and how to do it for the three simulations with, to remind you, worth 10% of the grade. Some procedural comments at first. You're supposed to create a Word document, send it into my graduate assistant Jennifer, who will then grade it and hopefully give you some comments, which will then allow you to fix it up to get a higher grade if you choose. And I tend to mark this pretty generously. I don't want perfection; just want to see that you're doing it. Now, what's the purpose of these simulations? Well, there are three purposes. One is to get you to practice Excel, which is important for this class and generally business education. Secondly, um, secondly, I want you to understand the concepts of statistics from a practical point of view. In other words, you'll be comparing the theory to what you actually see when you create the numbers that are generated by the simulation. And there's a third reason why I'm doing this, which I forget at the moment, maybe to torture you. I don't think that was it. Um, to teach you about the concept of a simulation. That's important as well, that you can simulate some of these ideas by just drawing random numbers. Anyway, let me share the screen so you can see the simulation itself that I'm referring to. We can open it here and here, and I think it's here. And here's the simulation one. Well, chapter 11 referred to an earlier textbook, but this simulation refers, and not textbook, is basically chapters 5, 6, 7, etc. Okay, so again, this is found in the tab system simulation assignments. So let's discuss this. Okay, so when you do statistics, you take a sample from a larger population. Now, why do you do that? And the answer is simply practicality. You can't access, let's say you're trying to do a study of the weight of all the people in the world. You can't access 8 billion people. It is simply impossible. Um, uh, you can access the 300 million people in the United States, 330 million, I believe. You can't access the 8 million people in New York City, or the 4 million people in Brooklyn, or even the people in St. John's University. I think there are 20,000. So you're forced to take a sample for practical reasons. Hopefully the sample is representative, and one way of doing that is by having a random sample, which is a discussion in its own right, important discussion. But you take a sample, and hopefully the average of the sample, assuming we're interested in the average of the population, like the average weight of all people, the average age, the average income, the average number of children, hopefully the sample is representative, and the answer you get will be not perfectly the same as the whole population, because that's unlikely, given that 100 people can't represent 100 million people. But it does turn out to be pretty close. You can do a survey of 1,000 people, 1,000 voters, and make a pretty good prediction as to what the whole country of 100 million voters. It's credible, important, powerful concept. Now, in order to evaluate a sample, we need to know the properties of the sample, namely the sampling distribution, meaning that what would happen if you take not just one sample, which is what you actually do, what if you conceptually took many, many samples from the same population? Now, in real life, that's too expensive to do, but we can do it on the computer by simulating it. And the population that I'm going to deal with is easy to generate, and we actually know the answers before we start, so we can see how close the sample averages are to the population. And imagine we had, I don't know, a million zeros, a population of numbers that run between 0 and 9. There are 10 million of them. A million zeros, a million ones, a million twos, a million sevens, a million eights, a million nines, 10 million numbers. Now, if you took all those numbers, put them in a pot, so to speak, or like a ping pong ball with each number on it, in a giant, giant box of 10 million ping pong balls, what would be the average of the entire box? Well, you would think, I mean, you can prove it mathematically by the formulas you learned about in chapter 5, I believe, but common sense, the numbers go between 0 and 9. They're uniformly distributed. There's an equal number of all of them. So you'd expect the average or the mean should be somewhere in the middle. In fact, exactly in the middle, 4.5 between 0 and 9. Slightly more, it's hard to predict this, but based on formulas also in that chapter, you could predict that the amount of spread, because it's not every number is going to be 4.5. It's going to be a 6 or a 2 or a 1. What is the spread among those numbers? Measured by the standard deviation, and it turns out the standard deviation of the population happens to be 2.87. Now, if you took 1,000 numbers from that group, what would you expect to get? All mixed up numbers. Well, hopefully it'll be close to the ideal answer of 4.5, but you may get 4.6 or 4.3. Now, what if we took a smaller sample of 5 numbers? Again, we'd expect the average to be around 4.5, but you may get 4.8, 6.2, 6.4, 2.2, 2.6. The numbers will run all over the place because with a small sample, one number can throw off the whole average. Well, to teach you about that intuition, I'm going to actually ask you to pull 5 numbers from that population between 0 and 9 randomly without physically having to do it by doing it on the computer, calculating the average, and repeating that process 200 times. So you have a good set of random averages from the population that we're looking for, each with a sample from a sample of size 5. So let's do that. I'm going to now open up Excel. By the way, this is the 3rd time I'm doing this. Somehow it didn't record the first 2 times. I'm hoping this is recording. Now, the formula, you start out with equal, of ran between, right, it's spelled between, ran between 0 and 9, has the computer pull out a random number between 0 and 9. In this case, the computer picked 2. If I repeat that process 4 more times by dragging it, each time you touch it, it changes the number, which is frustrating, but indicates that it's truly random. Well, you'd expect you get 5 random numbers. If you want to get the average of these 5 numbers, you say equals average. Now we expect it to be around 4.5, but what did I just do there? Edit equals average parenthesis A1 through E1. 4.2, not that far from 4.5. And if I drag it down 200 times, I'll generate the numbers that are the basic foundation or the raw material for the simulation. But I'm not going to do it 200 times. I'm going to do it 20 times. And we see these averages as you'd expect to get. Now, there are 4 jobs you have to do with these 200 averages. Again, I'm using the example of 20. I want you to calculate the average of the averages. Now, again, common sense would indicate that it should be around 4.5. So let's in theory predicts that, and common sense, and let's see it empirically or practically by doing the simulation by using the average formula applied to these 200 numbers. Secondly, I'd like you to turn these numbers into a picture. Well, you can do that by graphing a histogram, for example, where the numbers can be, let's say, 0 to 1, 1 to 2, how many between 3 and 4, 4 to 5, 5 to 6, 6 to 7. And according to the central limit theorem, you'd expect to get a bell-shaped curve. It's common sense, it's mathematically proven, and let's see if we can verify it by actually physically doing it. Thirdly, I'd like you to calculate the spread among these averages. They should all be around 4.5, but of course they're going to vary because the numbers are random. But what is the predicted amount of spread? Well, that's called the standard error of the mean. The formula that you learn about in this chapter is equal to the sigma, which is the population standard deviation, which we just said is 2.87, divided by the square root of 5. and that ratio comes out to 1.28. So when you calculate the standard deviation, if you got something close to 1.28, like 1.31, 1.35, 1.20, you know you did it right. And finally, I'm going to ask you to calculate probabilities based on these numbers. Well, how many numbers are bigger than 6.3 just to pick the number at random? Well, you can go down the list and see how many are bigger than 6.3. Well, here's one. Here's another one. And that comes out to 2 out of 20, which is about 10%, exactly 10%. And then I want you to verify it by the theoretical calculation. You learned how to do this, I believe chapter 5 or 6, using the StatCrunch normal distribution calculator, or you can do it in Excel, for those of you who followed with the book using Excel, or go to any calculator on the internet. You plug in the mean, which theoretically is 4.5. Don't plug in your own personal mean. I want this to be a theoretical calculation. You plug in the standard deviation among all the means, which we just said was 1.28. And you plug in the boundary, which is 6.3. And how many of those, what's the probability of getting bigger than 6.3? Well, let's say it comes out after doing the calculation. I'm going to pick a number close, like 7%. Well, we're getting 7% as the theoretical answer. And you saw, let's say, 2 out of 20 or 20 out of 200 of 10%. Well, 10% and 7% are pretty close, and that's another way of verifying this theory of this chapter. Now let's go look at it concretely, if I can find this here. It's here. So part 1, again, this tells you how to send it in. Part 1 says pick the numbers. We just did that. It's over here. Part 2, calculate the 200 averages, which we just did here, partly. Calculate the standard error of the mean. No, I'm sorry. Calculate the actual practical. I'm sorry. Calculate the averages of these 200 numbers. Get the averages, which should be around 4.5. Calculate the standard deviation among the averages, called the standard error of the mean, which is 1.28. So by plugging this into the standard deviation formula. Calculate the picture, the histogram of the 200 averages. Talk about, and you can get the answer to this question by either using ChatGPT, using your common sense, watching my videos I made about this, the YouTube videos, or by thinking about it. But anyway, I'm going to mark it pretty leniently. But I want you to write down why you expect to get a bell-shaped curve with these parameters that we saw before. And now the probability. How many are bigger than 6.3? Well, you can do it either by counting them, which we did briefly. You could do it by going to the Z calculation, which is another name for the normal distribution calculator. But the two of them should be similar. Then I want you to discuss this formula, again, using common sense. Why is the standard error of the mean, which is measures the variability among the averages, why should that be equal to the spread among the original numbers, in this case between 0 and 9, and depending upon the sample size, which in this case was 5. Why would you expect that the bigger the sample size, the smaller the variability? Why would you expect that the larger the variability of the population, you get a bigger variation among the averages? Again, it's kind of commonsensical. I do talk about it on some of the videos. Do your best at trying to write that down. And that is simulation 1. And I'll stop here and try it. Of course, you always have the opportunity to ask questions. Send me what you wrote. I'll check it out, talk about it, discuss it with you. Good luck.